Welcome everyone to the second lecture in our series on space optics. Today we're diving into the fascinating world of free space optical communications. Imagine a world where we transmit vast amounts of data across the emptiness of space, not with radio waves, but with laser beams. That's the essence of free space optical communication. But what makes free space optical communication so special, and why it is becoming a critical technology for both terrestrial and space-based networks? Let's find out. Buckle up, because we're about to go deeper into the fascinating world of free space optical communications, or FSOC for short. In this module, we'll build a solid foundation in free space optical communications by exploring its fundamentals. We'll dissect the free space optical communication chain compared to traditional radio frequency communication and delve into the essential link equations and budget considerations. We won't stop there. We'll uncover the secrets for choosing the perfect wavelength for your FSOC system, and then we'll shine a spotlight on the heart of it all, optical sources. We'll get up close and personal with lasers and photodiodes, the warhorses of FSOC. But sending a signal is only half the battle. We'll dive into the world of modulation techniques, understanding how to shape your data for transmission. We'll cover everything from baseband modulation to the nitty-gritty of OOK and PPM techniques. And of course, we'll touch on CCSS standard that guide our way. No FSOC adventure will be complete without understanding the challenges it faces. We'll tackle channel effects head-on, exploring weather conditions, the mysteries of turbulence, and how they impact your link performance. And finally, we'll demystify detection and signal processing. We'll compare different detection methods, learn about photodetectors and transimpedance amplifiers, and even get a handle on bit error rates. We'll round out our journey with a look at acquisition and tracking techniques, including signal acquisition, point-ahead angles, and the ever-important scanning process. By the end of this module, you'll have a solid grasp of the SOC technology, from its fundamentals to the real-world challenges it faces. You'll be well equipped to design, analyze, and even troubleshoot a SOC system. So let's dive into unlock the power of the light for communication. Let's take a closer look at the heart of free space optical communications block diagram. Well, we know that our system will be composed at least from three parts: transmitter, atmospheric channel, and receiver. Let's analyze each of them one by one. So, data source, this is where our journey begins. The information we'll transmit, this could be anything from simple text messages to high-resolution images or even scientific data. Afterwards, we have channel encoder. To ensure reliable transmission, we add a layer of protection to our data. This block uses techniques like error correction codes to make our message more resilient to noise and interference. Afterwards, we have a modulator. Here is where the magic of free space optical communication happens. This block takes our encoded data and imprints it onto a light wave, typically a laser beam. This is similar to how a radio transmitter modulates electrical signal onto a radio wave. Afterwards, we have an optical source. This is our beacon in the darkness of space. It generates the intense focused beam of light that will carry our data across the vast distances. Afterwards, we have pointing acquisition and tracking system. This clever system ensures our laser beam stays locked onto its target. It uses a combination of fine steering mirrors, feedback loops, and sophisticated algorithms to maintain a stable link even in the face of vibrations, atmospheric turbulence, or the relative motion of the transmitter and receiver. Afterwards comes atmospheric channel. So our modulated light beam travels through free space channel, which is simply the open air or vacuum of space. This channel introduces challenges like atmospheric absorption, scattering, and turbulence, which we'll discuss in more detail later. So afterwards, we have receiver side. Well, first we have an optical receiver, which is photodetector. On the receiving side, this device acts like an eye, capturing the incoming light beam. It converts the faint optical signal back into electric current, which carries the original information. Afterwards, we have amplifier. This block boosts the weak electrical signal from a photodetector, make it strong enough for further processing. Afterwards, we have demodulator. Think of this as the decoder ring for our light messages. It extracts the original data from the electrical signal, reversing the modulation process that occurs at the transmitter. Afterwards, we have channel decoder. The final step is recovering our message. This block uses the error correction codes added earlier to detect any correct any errors introduced during transmission. Finally, we arrive at our destination. The original information is ready for use, whether it's displaying an image on a screen, controlling a spacecraft, or unlocking new scientific discoveries. This diagram gives you a simplified overview of how free space optical communication link works. In this module, we'll dig deeper into each of these blocks, exploring the different technologies and techniques used in real-world systems. By then, you'll have a thorough understanding of how to design, analyze, and optimize free space optical communication links for a wide range of applications.